So, as we told in the previous video, our intention is to calculate how the energy is distributed in various microstates of this canonical ensemble. That is our immediate aim, which we should be calculating. So, for that purpose, we have defined this canonical ensemble system with a constant energy, with a fixed energy 0, and an ensemble inside, and an element inside, right? Right. Now let's assume that PR is the probability for the system to be in to be this system A, right, and to be in the energy value ER. So PR is the probability for that system A to be in the energy ER. So ER can have any value. So it can be E1, it can be E2, can be E3, but at one instant you have only one of those energies, right? But at the next instant it can of course change because it is exchanging its energy with the reservoir. So PR is the probability for what? PR is in other words, the PR is the probability for energy for the system A, for the element A, to be in energy ER T. So that is the point. A is in the energy ER T. That is the point. Now, similarly, you can have if we take the reservoir, it can be in any one of the large number of states with energy ER dash. So ER dash can be in any of the energy states, but that range is bigger, that energy is bigger. So it can be in any of the energy states of ER dash. The number of states of the reservoir, number of states of B, omega dash ER dash. It's a huge number. It is supposed to be a huge number, right? Since the reservoir is that many, obviously the number of microstates inside that also will be too many. So therefore it will be a big number, omega dash ER dash. So now this PR, right? What is the PR? PR is the probability for the system A to be in the energy ER. I can always write PR is directly proportional to omega of ER. But I will be more correct to write, or equally right to tell, PR is directly proportional to omega of ER, omega dash ER dash. Why? Because because the omega dash er dash is much greater than omega of er. So therefore it is more accurate to tell in terms of a bigger number, because my error will be lesser in the second case. But actually they are equivalent, because whatever is being lost is being lost to the, whatever is being exchanged is exchanged to the reservoir. So they are complementary numbers. Omega er or omega dash er dash, they are complementary numbers. So I can always write PR is directly proportional to omega dash er dash. Right. Now I should be able to tell or I should be able to expand the function omega dash er dash because then only I will be getting an idea of that function. So basically this omega dash er dash is a rapidly varying function, right? Omega dash er dash is a rapidly varying function. So if I need to know or need to simulate that value of omega dash er dash, I should be doing some kind of a mathematical tool to explore that. But what we will do is that we will not expand the omega dash er dash, but instead we will expand on ln of omega dash er dash. The reason is that, as we know, this omega dash er dash is a rapidly varying function. But it will be more accurate, it will be more convenient to work with a slowly varying function. So what we did is that we will just take the logarithm of omega dash er dash, so that we built in a slowness into the variation in the omega dash er dash. For example, if I so normally how do you expand a function? We have the best way is to explore the Taylor expansion. Taylor expansion series, right? So one can use a Taylor expansion series and try to expand this one. But Taylor expansion series can be applied for omega dash or the ln of omega dash er dash. It doesn't matter. But when we are trying to approximate a polynomial, like in the Taylor series, what we do? Basically, Taylor series is trying to approximate a function to a polynomial way. You know the kind of expansions. For example, you have the sin x or the cos x. So this is cos x, right? So if I need to do this one, the Taylor expansion, or any expansion for that matter, and if I need to know if it is a very fastly varying function, it becomes really difficult for me, because what I do, if you remember the Taylor series, what I do is that I take the expansion at this point value of at this point, and then I, for the next term, I take its differentiation, first differential, which will give me which will be given by my slope, and then for the second term I take the rate of change of this slope. That is how I take the second differentiation, third, fourth. So right, dy by dx, d squared by dx squared, d cube y by dx cube. So all those things I take, and I go on building up the higher order terms in a Taylor series. That is how I do it. But ln will help you to make this variation slower, so that my error will be lesser. So I use the ln. So okay, so we are going to apply the Taylor series expansion to ln of omega dash er dash. So what is the Taylor series expansion? Remember that f of x is equal to f of a plus f dash a by 1 factorial x minus a plus f double dash a 2 factorial x minus a the whole square plus etc. Right? It goes on to the f triple dash a x minus a the whole cube and all those things. So this is the general form of the Taylor series. So and you will remember that the Maclaurin series is a special case of the Taylor series, where you have you have the expansion about 0, which means that you have a is equal to 0 in this function. A is equal to 0, then you will get the Maclaurin series. But here you have the x and a, right? I think you will remember this. Right, what is that? So basically, I have something like this, and I have the x changing, because I am trying to I'm trying to simulate a function into the best possible polynomial, so that I can just be I can be in agreement with that function. I'm trying to simulate that function. So, for example, if this is my function, and I'm trying to take the expansion, say at a point A, right? At a point A. So I always take, this is the x, x is keep on changing. I mean, x, this is the whole value of x, and I take a point A. So first of all, what I do is that I take value up to here, fa, right? If I need to simulate for the next value of over here, I consider always a area like this. So and this will be my x minus a, right? Because in the x I move this much point, so that I take the expansion about a. So you can always go back to your Taylor series, which you must have learned in your BSc physics, probably BSc classes. So you can always go. So that is how so this is the way the Taylor series gets built up. So here we can have the similar the expansion for ln of omega dash er dash. So how do I write it? Ln of omega dash r dash, which can be written as equivalent to ln of omega dash E0 minus ER. So this is the same thing, right? Because ER dash is equal to E0 minus ER. So I can, now I apply the Taylor series expansion there, which is equal to ln of omega dash E0, right? Because my, that is the whole value of E0, right? And the energy, dou ln omega dash by dou E dash plus higher order terms. So that is how it builds up, right? So we have just converted this expression ln of omega dash r dash. We have just expanded it in terms of the Taylor series, right? I hope you understood that. So this is the similar equation here. Here we have the E0, which is building up here. So if my function is something like this, but here the criterion is that my E0 is the ultimate value, right? Ultimate value. Therefore, obviously, if I am expanding about E0, right? Which means that what? Which means that my A in the Taylor series is E0. And x is equal to, sorry, I did a mistake. That's why. Yeah. So the ER dash. The scale is ER dash. The biggest value of ER dash is E0, right? Yeah, I just got lost. So biggest value of ER dash is E0, and therefore, but I am expanding about E0. So if I am expanding about E0, A is equal to E0, X is equal to ER dash, and then in that case I can write it like this. Expand like ln of omega dash E0 plus dou ln omega dash by dou E dash ER dash minus E0 plus higher order terms. That is how you expand that. Now what? Okay, remember that we have introduced obviously an additional term of ln. We will not forget that. We will continue in the next video.